Hi everyone, it's Judy. Welcome back to the OnTrack podcast. Thank you for joining us today. Today we speak with Dr. Eric Bogatin, who's the Dean of Signal Integrity at Teledyne LeCroy. Eric has agreed once again to be a keynote speaker at AltiumLive in San Diego, October 9th through 11th. We hope that you'll be able to join us. It's going to be fantastic. So Eric talks about his keynote talk, but he also discusses the courses he teaches at Colorado University Boulder, plus some books he's writing, the makers he serves. There is no grass grown under this man's feet. I think you're going to enjoy hearing from Dr. Eric Bogatin. Welcome to Altium's OnTrack podcast, where we talk to leaders about PCB design, tackling subjects ranging from schematic capture all the way to the manufacturing floor. I'm your host, Judy Warner. Please listen in every week and subscribe on iTunes, Stitcher, and all your favorite podcast apps. And be sure to check out the show notes at altium.com/podcast, where you can find great resources and multiple ways to connect with us on social media. Hi, Eric. It's great to see you. Thanks for joining us again on the OnTrack podcast.
Hey, it's always a pleasure to join you on these kinds of events, Judy.
So, for those that may have missed your past podcast, why don't you give us a brief overview of who you are, what you're up to, and also a little bit about Teledyne LeCroy?
Sure. So let's see, I've been involved in the signal integrity, power integrity field for, too many years, back when I used to have hair and none of it was gray. And I've been involved on multiple sides of the fence. I got my start in the R&D environment, and then I worked in product development. I ran a couple groups when I was at Sun Microsystems from the user side, and then I switched over to the tool development side, working for some software companies. And then I realized that there was a strong need in order to kind of create the market for some of these software tools that were useful in analyzing signal integrity problems. There's a strong need to help engineers understand what the problems were that these tools solved, and that was kind of how I got involved in the education side of things. And it's always been one of my interests, and been doing this for about 30 years now, doing training, education, development for engineers in the industry. And I had my own company that I started with my wife Susan. We would literally go around the world and do training classes. I wrote a couple of textbooks in the field, and then about 10 years ago, LeCroy acquired my company, and I continued doing training through LeCroy, and then of course LeCroy was bought by Teledyne, so I'm part of Teledyne LeCroy now, and recently I've started focusing. So what I have been doing over the many years has been focusing on best design practices. How do you, the vernacular in the industry is, how do you get it right the first time? Mm-hmm. How do you design the product so that you eliminate the potential problems that will arise before they happen? And of course, that's the way you want to do it. That's the way a lot of companies try to do it, but not always are we so successful. And sometimes it doesn't work the first time, and so the goal is, when my boss at LeCroy says, then the goal is to get it right the second time. and that's where measurement comes in. So you use measurements to analyze your product to find the root cause. And so in the last few years, I've been focusing my attention now on what we call best measurement practices. How do you use scopes and other instruments in order to analyze a product to find the weak links, and if it's not working, to find the root cause. So that's where most of my interests are right now. Is I still pay attention to best design practices, and that's what I am teaching at CU. But I am also spending time on best measurement practices because I think there's just as strong a need, if not a larger need, to provide some guidance for folks that are using instruments in how to get the most value out of those instruments.
Makes sense. Makes perfect sense. Well, we're delighted that you've agreed to come back for a second year in a row second year in a row to be a keynote speaker at AltiumLive in San Diego, October 9th through 11th. So I wanted to talk a little bit about that, as well as a breakout session you're going to do on the topic you were just mentioning, which you're going to be doing, called Mastering the TDR in 45 Minutes. So why don't you start off by telling us a little bit about what your keynote talk is going to be about?
Sure. Some very skilled person came up with a very clever name for the talk. What was it you came up with? What was the title?
Oh, Breaking Bad.
Breaking Bad, yeah. But it really kind of encapsulates the main message that, of course, I was thinking of a title like, on the internet, nobody knows you're a dog, or something like that. Because it's really this theme of there's a lot of stuff, a lot of designs that are posted on the internet, but there's no filter. There's no peer review for stuff that goes on the internet.
Exactly.
And so you download a design and you have no idea. Yeah, the guy that put it there, or the person put it there, says, "Oh, there's a great design. It works really super. I've used it, for the last 20 years. Here it is. I'm offering it to anybody." You have no idea. Well, does it really work? And are the design principles that are demonstrated in this design, are they really good things to do? Can I use those principles? Can I take a part of that design and use it for my next design? Mm-hmm. And so just because something is on the internet doesn't mean that it's a good design or valuable information. And when I've been teaching this class at CU for the last couple of years, one of the classes I teach is printed circuit board design. And so I've been looking at in detail at different designs, and thinking a lot about how do I articulate the right way to design the board. What are the best design guidelines for the circuit board? I've done a lot on the principles and how we apply the principles, but now I'm looking at specific design features in the board. And one of the examples that I look at with my class is the Arduino microcontroller. Mm-hmm. It's the workhorse microcontroller out there that has revolutionized the maker community. It has just empowered literally kids 8 years old to 80 years old to get into building things and making anything smart. It's really easy to use. And I did some estimates. So there are a number of vendors out there that make these little circuit boards, the Arduino Uno R3 version, and there have been something like 1 million of these boards manufactured in the last 10 years. Wow. So there are a lot of them out there.
Wow.
And they all use that Mega 328 microcontroller. Mm-hmm. And as a great micro is 8-bit. It's got some ADDs on it and a bunch of IOs, and really, really simple, easy to use, but it's still very versatile. Well, the design for all of these boards is the same one. I'm not sure SparkFun created it, but they have provided the design files open source. Mm-hmm. And most designs, most of the boards that I've bought, either domestically or offshore, most of those boards use the same layout as in that SparkFun is open source. And again, I don't know if SparkFun got that design and then just made it open source, or if they created it, but it's a very common design. And when I first looked at the artwork for it, and you can get a board, hold it up to the light, and you can see through it, because you realize it's a 2-layer board, and there are some gaps in the plane. And you look at the board, and there's copper fill on both sides, but it's not continuous. You look at it through light, and you can see the gaps in the planes. And that's always an indication of, without doing any measurements, I can tell there's going to be ground balance problems in that board. And sure enough, we use that board in my class as an illustration of what the signature of ground balance looks like, because it is so prevalent in that board, that it was the design guidelines that were used to design that board was one that is very commonly used, which I think is not a very good design guideline, and it is when in doubt, throw copper at the problem. And that's basically what copper fill is. That there are right ways and wrong ways of using copper or
Yeah.
copper core on a board,
Uh-huh.
and most of the time they're implemented in the wrong way.
Mm.
And so on this board, basically you get the components that you place them on the board. You do the design for connectivity. You route all the pins that need to be routed, and then you say, okay, now everything, and it's not routed on one layer, it's routed on two layers, and the traces go back and forth because of crossovers, things. And after the traces are routed, then you do, okay, copper pour on the top and bottom layer, and you say, well, there's copper, then that should be all I need to do. What can be wrong with copper? Well, the design has terrible return path control. And so I use this design in my class to illustrate how not to design a two-layer board. And here it is, one of the most popular open source designs out there that, and it works. I mean, it's really hard to, it is possible to find an application where the noise that's generated breaks the code, but it's really hard to arrange that because it is an incredibly robust design. But if you use that design as an example of, this is what everybody is doing, there are a million of these boards, it must be the right way. If you use the principles that you see in this design of this board to design your next board, that's when you potentially could fail.
Right.
And
it's
so
it's like embedding then poor habits.
It's exactly it. It's habits.
Yeah.
And what I try to teach in my class is, if you can do something in the design that doesn't add a cost and doesn't influence anything else, if it's free and it will improve performance, it's always a good habit to do.
Right.
And so you pick up bad habits in using open source designs unless you the designer take responsibility for ownership of, is this designed well? And so in my in the keynote, I'm going to talk about some of my experiences teaching this class at CU, and how we use the Arduino design to show this is how you can measure ground balance. You write a little bit of microcode. So this is one of the cool things, is the Arduino is so easy to use. My students, I have mixed a few juniors, mostly seniors and graduate students, some of whom really are not embedded designers, so writing code is a little bit new for them for microcontroller, but it's easy enough that they can do it literally in one lab. And so we write a little code to adjust the I/O to switch n number of them simultaneously, and then we measure them with a scope in a way to minimize the artifacts of the measurement, so we can see the switching noise on the scope screen. And we do that for the commercial off-the-shelf Arduino boards, and then I have my students redesign that same board with the 328 microcontroller, but implementing the right habits, the right design guidelines. And they're really maybe 7 altogether. And I did an article for Signal Integrity Journal where I provided the list of, here are the 7 top design guidelines or design rules to follow for a 2-layer IoT kind of application. And I'll go through those in my keynote. But the students, they redesign the board 2 layers, so it's no extra cost. Same form factor, same pins and same header pins and everything, but just designed well to control return paths and to minimize the routing inductance to the decoupling capacitors to the microcontroller, so the signal paths are done well, power delivery is done well, and then they use the same code to drive their design with the same I/O switching, and they measure the switching noise, and darned if they don't find about a 90% reduction in the switching noise.
Wow. And
unfortunately this project is the second one they do, and it happens they finish this around the 10th week of the class, and that's when everything comes together for them.
Yeah,
that's what they said. Oh my gosh, all these things you've been telling us, I can really see it here. It really works.
What a great, tangible example to apply all those principles, right? In real life. It's frightening, though, to me to think about so many, hobbyists or, makers out there, that maybe want to move ahead, or professionals that are using Arduinos for prototypes that are maybe EEs that don't have a lot of layout experience. And then, like you said, take these bad habits and carry them forward. When you have such a major installed base out there of this
Right.
platform, it's frightening to think of the implications. So, I think kudos to you for bringing that to your students. And I can only imagine the light bulbs that go on in their eyes, lighting up.
It's part of it is that they did the design, that they did the measurement, and so they make that visceral connection with it.
Right.
And you're absolutely right. You can literally see the light bulbs going on when they do the measurement. The first thing they do is they double check, am I measuring this right? What happened to the noise? And because I teach them about artifacts and watch out for artifacts, and if it's not what rule number 9, if it's not what you expect to see, there's always a reason for it. And they expect to see a lot more noise, and they don't. And they really work hard to verify that, gosh, there really is such a low amount of noise. And these 7 design guidelines, they apply not just to Arduino, which is a great application,
Right.
but I think almost all IoT applications that are 2 layers. I mean, you can extend it to more layers, but there's so many IoT designs that are 2 layers, and I think we need to don't apply. And so that's really the message of the keynote: is don't apply what you see in this popular open source design and think that this is the right way of designing your boards in the future.
My friend Julie Ellis, who's an FAE at TTM, she always likes to say in her classes that it's a myth. There's really no such thing as a quick and dirty prototype.
Well,
you'll pay for that sucker later.
Right. And so here's the distinction that I make. And this is where maybe it's the boundary between kind of the maker community and the world of professional engineers. If your design works in a solderless breadboard, so as you get one of those little white solderless breadboards, you plug your 8-pin or 40-pin dips with 100 mil centers. You plug them in there. You get your wire straps and or the jumper wires, and you plug them in all over the place. If your design works in a solderless breadboard with a bunch of jumper wires, then the interconnects are basically transparent. It doesn't matter how you design the board. You just design your circuit board for connectivity and maybe for assembly and for manufacturing. But it doesn't matter what the interconnects look like. And I think in a lot of maker applications, that's the case.
Right.
Because you're not pushing the limits, you're not pushing clock frequencies.
Simple.
Right. 8 megahertz is great. Throw a couple op amps on there maybe, or some other H-bridge motor drivers, and it's fine. It's when you're really pushing the envelope, where you want to get the high data rate, where you want to get the power off and on, the power management, so you minimize the power consumption or energy consumption. It's where you're using not a 8 megahertz but a 600 megahertz M4 Cortex microcontroller. It's when you go beyond the maker space into the professional engineering world, that's when interconnects matter, and that's when a lot of these good habits are really, really important.
Well, and to your point about the IoT, I think the last figure I saw says there's about 25 million IoT connected devices out there today, and in the next, 5 years, there's going to be like 75 million. I mean, there's a proliferation.
I think that's a B. It's a B.
Billion. Sorry.
Yeah.
Yeah. What am I talking about? Billion.
Yeah. I probably have 500,000 in my lab right here.
Yes, I did mean billion. Thank you for catching that. So, yeah, especially at your house, Eric Bogatin. And so, so with those,
you're absolutely right.
That many billions, the proliferation of IoT devices, and I think that idea of doing a quick and dirty design, I think that is sort of a myth, and that's going to bite somebody. So, so for our listeners, Erica and I were on the phone, and we were talking about, well, what shall we call this thing? And I am thinking of it, breaking bad habits. And as he was talking about it, I said, we got to call it Breaking Bad, to break those bad habits. So that's what we ended up naming it. We had a chuckle over that. So, hopefully this will keep you from, forming those bad habits, and then carry the good habits with you, forward into future design. So, and Eric, I think I mentioned to you that Bob Martin will be there also as a keynote from Microchip, and I can't wait to just put you two together and just stand there and watch.
Well, I'm very much looking forward to meeting him, because he he's one of my heroes. I mean, the Atmega microcontrollers have just revolutionized the maker community, and I think the progress they've made over the years and the continual support to the maker community has been really, really valuable. And while I spend most of my time working with professional engineers, I also do some work in the maker community with our local hackerspace, teaching Arduino workshops, and because I think it's so important to get more people involved in this kind of easy to use, low cost electronics.
I call it the gateway drug.
Yeah, you're right. It is. It is.
Well, I think it's about exposure. I've said that here many times, but this is how we get kids turned on, and find out if this is something that's compelling and interesting to them, and is exposure. And being that these things are easy, really just opens the doors, which is so exciting. So tell us briefly about your class in mastering the TDR in 45 minutes.
Yeah, so right after the keynote, I'm going to be running over to the other room to talk about TDR measurements. So this is part of my interest in best measurement practices. And the TDR is, I think, the most valuable instrument in order to characterize as a first pass electrical properties of circuit boards. The two most important things you get from a TDR is how uniform is the transmission line on the board, and what is the characteristic impedance. If it is uniform, what is the characteristic impedance? And so it's used a lot in production to validate the impedance of the board, but it can be used in so much more back in the lab. I mean, you use it in production to verification of the lot. You test a coupon, but if you bring your board back into the lab environment, then you can now use it to help you analyze some of the design implementations. Because really, the TDR, it sends the signal out. It encounters and kind of senses that instantaneous impedance the signal sees each step along the way, and if that impedance changes, then something reflects, and we get that coming back, and that's what we measure. But that's exactly what a signal does as it's propagating from a driver onto an interconnect to another receiver. And so the TDR gives you this really quick way of emulating what would happen to the signal quality as it propagates down the interconnect, and where does it encounter discontinuities that can cause distortions. And so we're going to look at how do we think about that signal propagating on the interconnect, how do we think about where the reflections occur, what things cause reflections, and then how we use the TDR to help us emulate, well, what would a driver see as it sends the signal down? Because the TDR I'm going to bring in is pretty versatile, and we can change the rise time, and we can look at what happens to I find one of the biggest sources of discontinuity is the launches, either when a cable interfaces to the board, or cable plugs into something else, or when the driver, the IC, connects to the trace on the board. All those launches are the biggest source of one of the biggest sources of discontinuities, and we can use the TDR to emulate what would the driver see at different rise times as it sends the signal down. And one of the most important rules in design of interconnects is, if you can't keep it uniform, keep it short. And we'll see that if you have a short discontinuity, like at the launch, that hey, if your rise time is long enough, it becomes transparent. it disappears, it smears out. But unfortunately, on the other hand, as we get to shorter rise times, as devices shrink, rise times decrease, what wasn't a problem suddenly becomes a problem because you get a lot of reflections from it. And so we're gonna look at how do we analyze, how do we think about signals propagating on interconnects, how do we interpret the measurements from the TDR, and how do we use it to help us explore and test some design ideas from circuit boards. And we'll look at single-ended and differential signals on interconnects.
Awesome. Sounds like a great class. And to look at things sort of preemptively, once you're measuring out manufacturing, you can't do anything about it then except throw it in the scrap heap.
Yeah. And that's why you do it for verification, but for design, you want to do it as early in the design cycle as you can.
Yeah, makes sense. So, as always, there's no grass growing under your feet. I don't know how you keep all the plates spinning you do, but beyond what you do at Teledyne LeCroy and measurement and the teaching and the makerspace, you're also a professor at CU Boulder. And I think that you mentioned now you are writing a textbook. So why don't you catch us up on the list of things, the things that you're up to, sort of outside of the LeCroy work that you're doing?
Sure. So so with LeCroy, I'm focusing on the best measurement practices. At CU, I teach in the fall a course on circuit board design, and that's what I'm basing my the Keynote on. And then in the spring, I teach a course on high-speed digital design. So it's really about signal integrity, kind of the next step of worrying about transmission lines, reflections, terminations, all that kind of stuff. But from a very practical perspective, rather than a bunch of Maxwell's equations with different boundary conditions. There are other classes that are taught at CU that cover that topic. I try to focus on the practical aspects of transmission line design. And then, so for both of those two classes, I'm also working on textbooks for them. So I've got a draft of textbook for the circuit board design class that I'm using in the class, so the students are helping me kind of debug the textbook and clean it up. I hope by the end of this semester it'll be clean enough to start passing around and focusing.
Exciting.
And then, and so it's not so much about here's how you lay out a board. It's here's how you go from, the working title is how you go from a back of the napkin sketch to a working widget. And so it's really about the design process and about how do you build the schematics, select parts, move them over to the layout, do the placement, do the routing for connectivity, for signal integrity, for power integrity, for assembly, for manufacturing, and then about test and bring up. What do you do in the debug and in the bring up phase? What do you do in the test phase? And how do you use test equipment correctly? It's mostly scopes and power supplies. The other book is for the other class on high-speed design. I have a textbook already on signal and power integrity simplified that's been out for many years and is real popular. We use that in the class, but I'm writing another one for our tech house. So they're part of Horizon House, which publishes the Signal Integrity Journal.
Mm-hmm.
And so, since I'm technical editor at Signal Integrity Journal and kind of part of the family, and so they've been bugging me to write a book with them. So I'm doing a book on focusing really just on transmission lines. It's about some of the principles about signal propagation and what a transmission line does, design and characterization of transmission lines. So that covers the stack up and what are you trying to design for? How do you adjust geometry materials? How do you estimate? How do you use 2D field solvers to help you design? And then about TDR measurements, because that's really the workhorse tool to analyze transmission lines. So that again is associated with the second class, and hope to have that one complete actually the first part of next year.
That's exciting. Well, I'm excited too that you're working with Artec and Horizon House. We share those friends in common, and
Yeah.
I've seen a lot of the publications that have come out of Artec, and they're really nice. And I would love to see some of that available too to our professional community. Through a place like Artec, so that's great news. And by the way, I will make sure and share Signal Integrity Journal link here in the show notes, because Eric is also the editor of that magazine, and it's fabulous. If you haven't had a chance to read it, they also put on an annual conference called EDICon, and so if you aren't already connected with them, I highly recommend them to you. And another way you can read more from Eric and on signal integrity and so forth. So I think we are about out of time, my friend, but thank you so much for taking the time to tell us.
Before we go, can I plug 2 other events?
You sure can.
So part of wearing my Teledyne LeCroy hat, part of what I've been doing is creating a series of webinars. These are all free webinars about high-speed characterization of interconnects. And we have a whole series. The next one's coming up in September 4th, and we'll give you the link to put onto the show notes here. And then I'm also doing a public live seminar for Teledyne LeCroy in Milpitas, September 11th, and that's free and open to anybody, but seating is limited, so if anybody's interested, they'll want to click on the link you'll provide, and then be sure to register early.
Very good. I've been sharing whenever I see those pop up on my LinkedIn. I try to like them and share them. So another good way is to maybe connect with myself or Eric on LinkedIn, because those will also pop up on an ongoing basis there. So, and you're also going to be at PCB West, correct?
I am, yeah. So I'll probably see you and many of our mutual friends there.
Yes, that's coming up in the next few weeks. So also, if you are at PCB West, make sure to stop by and take Eric's class there.
Great.
Well, thanks for another great podcast, my friend. I can't wait to see you both at PCB West, and then I get to see you not even a month later, I think, at AltiumLive. So we've got some great events, and like you said, good friends to get together with and great learning opportunities. So look forward to seeing you then.
You bet.
Great. For our audience, thank you. Thank you for joining. To our audience, we appreciate you joining. Make sure to like, subscribe, and give us your comments so we know what to record here for you and keep you in the know. Also, AltiumLive registration is now open. It is filling up quickly, and September is going to be a big registration month. So I will also put that in the show notes here to make sure you get registered and signed up for San Diego, October 9th through 11th, or Frankfurt, October 21 through 23. Thanks again for joining. We appreciate you tuning in. We'll see you next time. Until then, remember to always stay on track.